We know that we have four quantum numbers that tell us about the position of electron around the nucleus based upon the orbitals, their presence in particular shell, and their energy order. Let's talk about the electronic configuration, which is the configuration of electrons in particular energy levels outside the nucleus. As every element has different number of electrons, their electronic configuration is also different, and the whole periodic table is based upon the electronic configuration. In order to fill the electrons in particular orbitals, certain rules must be followed. Electrons are filled in orbitals with increasing energy. The order of energy is S less than P, less than D, and then less than F. But this order deviates for third orbit. Keep in mind that every orbital can accommodate 2 electrons. You can fill only 2 electrons in an orbital. Mathematically, an orbital with n plus L value small will be filled first with electrons. If two orbitals have same n plus L value, then fill that orbital first whose n value is small. Keep in mind n is the principal quantum number and L is the azimuthal quantum number. The number of electrons in a shell or orbit can be found out by using 2n square formula. The principal quantum number for K shell is 1. Multiplying 2 with 1 gives us the answer 2. And we know that the K shell can accommodate 2 electrons. Same is the case with L shell, but now you have to replace principal quantum number with 2. And it gives the answer of 8, that the L shell can accommodate 8 electrons. For M orbit, the number of electrons that can be filled out are 18. You have other quantum numbers which are azimuthal quantum number telling us about the orbitals S, P, G, and F. Moreover, the P, D, and F orbitals are degenerate also. So based upon our learning, here is a table that tells us something about n plus L value. And this table is enough to understand that which orbital will be filled first. The closest shell to the nucleus is K, which has a quantum number 1. And for K shell, the subshell is definitely S. In writing the electronic configuration, you have to specify the orbit with principal quantum number at its left side and then writing the orbital in which the electrons will be filled. As far as the azimuthal quantum number is 0, so n plus L value is 1. As you know that every orbital can accommodate 2 electrons, so the 2 electrons of K orbit can be filled in 1s. On the other hand, for L orbit, the number of electrons are 8. While the principal quantum number for L orbit is 2, subshell for L orbit, which will be filled first, is definitely S, which has the least energy. 2 is representing that the S orbital is present in the second shell. For S, the L value is 0 and 2 plus 0 gives us the answer 2. It means if an element contains more than 2 electrons, the remaining electrons after filling the 1s orbital with 2 electrons will be accommodated in the 2s orbital because the 2s orbital has greater n plus L value than 1s orbital. This is what this yellow colored statement is saying. But the L orbit can accommodate 8 electrons and 2 of it are filled in 2s orbital. Remaining electrons are 6, which will then be accommodated in 2p orbital. For p orbital, the azimuthal quantum number is 1 and 2 plus 1 gives us the answer 3. As p orbital is degenerate, which has px, py, and pz orbital, and each orbital can accommodate 2 electrons. As the p orbital can accommodate overall 6 electrons by filling 2 into px, 2 into py, and 2 into pz. 6 plus 2 of 2s orbital make the total 8 electrons of L shell. The M orbit can accommodate 8 electrons. Now start filling the electrons in M orbit. The principal quantum number for M is 3. 3s is showing that the s orbital is present in third orbit. The azimuthal quantum number for S is definitely 0. 3 plus 0 give us the answer of 3. Now here you see that the n plus L value for 2p and 3s is same, which is 3. Now you have to fill that orbital first whose n value is small, as 2p has principal quantum number or n value 2 and 3s has n value 3. So you have to fill 2p first because it has small n value. The m orbit can accommodate 8 electrons and 2 of it goes into 3s orbital. Remaining are the 16 electrons. Now go for 3p. The azimuthal quantum number for p is 1. The principal quantum number will remain same. 3 plus 1 gives us the answer 4. As p can accommodate 6 electrons, 6 of 3p, 2 of 3s make total of 8 electrons, but 10 electrons of m orbit are still remaining. Now go for 3d, which has azimuthal quantum number 2. 3 plus 2 gives us answer 5. As d can accommodate 10 electrons, so 10 plus 6 plus 2, 18 electrons will be completely filled. Now see that 3d has n plus L value 5, while the 4s has n plus L value 4. Now here, focus on this statement that I have told you earlier, that for third orbit, the order of filling of electron in orbitals deviates. Why this order deviates? Because experimentally it was found that the 4s orbital has greater power of penetration. The s orbital of fourth shell penetrates into the third orbit and its energy gets lower than 3d. Therefore, the 4s will be filled first and 3d will be later. Mathematically, it is suggested that the orbital whose n plus L value is small will be filled first. 4s has smaller n plus L value than 3d. So 4s will be filled first and then 3d. This is how you can extend the whole table for every shell. Now understand the electronic configuration with an example. 1s has the lowest n plus L value. It is written first here. Here 1 is telling us about the principal quantum number or orbit in which the subshell S is located, and S is the subshell or orbital. It can accommodate 2 electrons which are written at superscript. An element having more than 2 electrons in it, the electronic configuration will extend, and now you have to fill 2s with 2 electrons because it has greater energy than 1s. And n plus L value of 2s is greater than 1s. And this is what I have told you earlier, that you have to fill the orbital with increasing energy. Mathematically, an orbital whose n plus L value is small will be filled first. And if two orbitals have same n plus L value, that orbital will be filled first whose n value is small. Then you have to fill 2s orbital with 2 electrons. Then 2p. Between 2p and 3p, you have to fill 2p first because it has small n value. As p orbital can accommodate 6 electrons, then you have to fill 2p with 6 electrons. Then 3s will be filled with 2 electrons, then 3p, and then 4s, because 4s has smaller n plus L value than 3d. 4s will be filled first with 2 electrons and then 3d will be filled with 10 electrons. This is not the hard and fast rule that you have to fill every orbital with exact the same number of electrons that it can accommodate. The number of electrons can be less than the number of electrons a particular orbital can accommodate. It depends on how many electrons are left behind for a particular element. And after that, you have to fill 4p orbital. This filling of electrons in orbitals with increasing energy is known as the Aufbau principle. This statement and this rule was given by the Aufbau. However, the p orbital is degenerate. What is the pattern of filling the electron in degenerate orbitals? This was given by the Hund's rule. It says that if degenerate orbitals are available, then you have to fill the electrons one by one in every degenerate orbital. For example, the p orbital can accommodate 6 electrons. You have to fill 2px with 1 electron first, 2py with 1 electron, 2pz with 1 electron first. Not the pair of electron is filled in 2px first, pair of electron in 2py, and pair of electron in 2pz. No, this is not correct. You have to fill single electron in every degenerate orbital first. The second electron will be filled later. The second electron in 2px will be filled after filling the 1 electron in 2px, 2py, and 2pz orbital. Horn's rule also says that the half-filled and completely filled orbital are stable. This statement stands out as a reason for the ionization energy of certain elements which are predicted to be higher, but experimentally it was found that the ionization energy of certain element is smaller, and the reason behind it is that the half-filled and completely filled orbital are stable, and every element tends to stabilize itself. In every orbital, 2 electrons are definitely accommodated, but they should be represented as the opposite spins. Two single-headed arrows anti-parallel to each other will be written at the superscript of every orbital, showing that the 2 electrons in an orbital have the opposite spin. This statement is such that the Pauli exclusion principle says that the 2 electrons in an orbital must not have the same value of all of the 4 quantum numbers. Here you see that in the 2px orbital, the principal quantum number for both of the electrons is 2. The azimuthal quantum number for both of the electrons is 1. The magnetic quantum number is 0, while the spin quantum number must be plus 1 by 2 for clockwise rotation of electron and minus 1 by 2 for anti-clockwise rotation. This is what the Pauli exclusion principle actually says, that the 2 electrons residing in the same orbital must not have the same value of all of the 4 quantum numbers. And this is actually the pattern of writing the electronic configuration.